Hi, everyone, and welcome to this edition of the Humans of AI. My name is Paul Cunningham. I'm a director of the Data Science and AI Association of Australia. And in this edition, we deep dive into autonomous driving with Dr. Stewart Worrall. Dr. Stewart Worrall is a researcher at the Centre for Australian Field Robotics. They are doing all kinds of really, really crazy autonomous driving research projects over there. And I was lucky enough to interview Dr. Worrall with regards to his particular work in the autonomous driving field. But yeah, in this talk we deep dive into the field. We cover ethics, we cover the algorithms, we cover sort of what Dr. Worrall's ideas are and the best way to solve some of the big questions hanging over the field at the moment. So yeah, with all of that being said, really excited to kick this episode off. So let's get to it.
All right. Hi, Dr. Stewart Worrall. How's it going? Welcome to the Humans of AI. Thank you very much for doing this podcast.
Yep, no problem. Thanks for having me, Paul.
So yeah, just for those listening, there's a bit of a construction going on in the background. So if there's apologies in advance for any background noise that might get picked up here, but we'll do our best to edit it out post-production. So yeah, Dr. Stewart Worrall was kind enough to present his work on autonomous driving at a meetup which we helped run at Tesla a month or two ago. And yeah, I reached out to Dr. Worrall to see if he would be keen to potentially do a podcast to elaborate on that work too. So yeah, we're lucky enough to have you here.
It's my pleasure. I love talking about this stuff.
Or to be in your office. So yeah, so of course, this is called the Humans of AI for a reason. And the reason is that I'd love to hear your story, essentially, of what drew you to the field and what got you interested in all of this. So it started off like when did you get drawn to technology in the first place? At like what age did you realize like this, tech was for you?
Yeah, good question. So I started when I was very young on computers, and the computers at that time weren't quite as everywhere as they are now. And so at that stage, this is before Windows 95, right? This is before these ones you're talking about with DOS systems and things like this.
Yeah, cool.
And so I can still remember when I was very young,
Can I ask which age they were? Like how are we like?
Well, I was born in 1980, so basically towards the end of that decade is when I started in computers. And the first time I ever wrote a program was when I borrowed a book from the library, an actual paper book from the library, which had program listings in them, which you would actually take home and type out yourself.
Yeah, getting rare these days, but yeah. Awesome.
It's not a very efficient way to do programming.
Yeah, sure. There's no internet, nothing.
Not at that time, no. Well, not that would be for everybody to use, no.
Okay. And what language was that?
Basic.
Okay, cool. Awesome. So Basic was your first language?
Basic was my first language, yeah.
Oh, cool.
A bit embarrassing to say, really, because it's not a great language, but it can be useful. It was used a lot at the time.
Right. Yeah. I think the first code I ever wrote was in Basic too.
Yeah.
So there you go.
Yeah.
I wrote I think it was a role-playing game, a text-based role-playing game.
Yeah.
In Basic. So fast forward a little bit. And when did you realize that you wanted to sort of go? Did you get started in autonomous driving initially, or did you sort of start in machine learning and then move towards autonomous driving? I
took a bit of a different path towards this. So I started I studied mechatronics and computer science, and as an outcome of that, there was a lot of work that we were doing at the University of Sydney in mining safety. So we were trying to work out ways to improve drivers' understanding of the world around them. And that led to fitting cars with sensors, fitting vehicles and trucks, the large mining trucks with sensors. And so my thesis was a lot of the work on my thesis was about how to improve situation awareness for drivers in mining trucks.
Right.
So there was benefits to working in mining because for one thing, it's a closed environment. All of the vehicles in there like have to be certified to be there. It's not like you have random people.
Right.
But the disadvantage is it's a really rough environment. It's usually very remote, very hard to access, and that made some pretty serious challenges.
Okay, awesome. So mechatronics, and then you moved from there. You moved into essentially like autonomous driving in the mining space.
Yeah, so we weren't doing autonomous driving at this stage. This was probably now 15 years ago when I was starting this one. But it's like I have never had really a career sort of jump where I've completely changed path. It's more like an evolution.
Yeah, sure.
So when we were doing the work in mining, the first thing we were doing is to try and give a driver a warning if there was something that was unsafe, or if they were doing something which was against what the rules of safety in the mine site was.
And then that was using machine learning to achieve that, or was that just rule-based systems?
So at this stage it was rule-based.
Yep.
At this stage it was rule-based systems. But a lot of the things that had to happen for this to work properly was that we needed to understand the context of the situation. So we had to learn, we would collect all of the data from the vehicles driving around the mine for a period of time, and we started to try and learn where the intersections were, where the points where the vehicles were doing interesting things were.
Sure.
And then sort of to use that to then take that context and then sort of give that back to the drivers to let them know what was going on.
Awesome. Cool.
And so then it sort of evolved. So then mining was one thing, and then all of a sudden, the industry sort of changed a bit, and our focus sort of shifted, and then we started moving to like passenger vehicles because it's a very similar problem. But effectively, it's just with smaller, more vehicles, but smaller vehicles.
Okay, cool. Okay, so hold that thought. I'm going to try to backtrack a little bit. So, and I don't know if this is right to do this, but you did your PhD, just so that people are listening, you did your master's in mechatronics still?
I did my PhD in mechatronics, yep.
So the whole thing. And what was your thesis on, if you don't mind me asking?
Yeah, so my thesis was actually on how to provide situation awareness in complex multi-vehicle environments.
Awesome.
So yeah, and it was like a natural progression to take sort of the outcomes from this one, which was a business. So it was actually a reasonably successful business for a while. We installed equipment into trucks. We actually maintained a lot of the job. I mean, my role at this stage, I had many hats. So sometimes I was, helping installers, and sometimes I was, technical selling to mining operations, and I was doing all sorts of different things at the time. So I got a lot of experience with like hands-on talking to drivers, understanding what their problems were, and understanding how sort of technology could sort of help them make better, not so much make better decisions as such, but understand better what's going on so that they can make better decisions.
Yeah, cool. I think that's like a massive, it's also like the whole automation of those mining trucks is like a huge success story for Australia in general, right? Like we were one of the first countries in the world to do it.
Yeah, no, absolutely. So up in I can't remember where the first ones were, but up in the Pilbara was a long time ago where they've had these trucks now. And they had many issues. And one of the things that sort of is very different in an urban environment compared to a mining environment is that it's very restricted in what can go in and out. So you can have all these trucks operating quite safely because no one's allowed in that area. And if they detect someone in that area, like the thing shuts down, they're not allowed to do that. So they don't operate around people. They operate just by themselves.
Right.
And the worst thing that could happen is that you could have a truck accident, which would be a big problem. But all the trucks belong to them, so they're all fitted out with the technology that they need to not hit each other.
Interesting. How do they detect if an intruder or whatever got into the space? Do you know? Or
yeah, I haven't been involved in that side of things directly.
Maybe I shouldn't ask this. Let's just pause this thought.
Well, no. I mean, I haven't been involved in that specifically, but they do have sensors on the vehicles to understand, because not everything is fitted with the sensors, right? With the technology which broadcasts the position and lets them know that way. So they have to be able to detect things in the environment as well, other than animals and other things as well in the environment too.
Cool, like kangaroos.
Yeah.
Or anyone else listening, this has been recorded in Australia.
That's right.
Also, how did you go from so mining, and then you moved into essentially like fundamental work on autonomous driving. So yeah. How did that transition happen?
Well, so many of the same technologies that we worked on in the mining environment translated very well into the urban environment. So, for example, mapping, understanding context, working on perception, localization, which is actually really, really challenging topic for like an urban environment, it's really, really quite hard to know exactly where you are, because you can't just use GPS to get a position. It's not possible to rely on that. And so a lot of those things led to research in how to make vehicle operations safer. And from there, once you start to understand where you are very well and understand what things are around you very well, then pretty much the next logical step at that point is to take control of the vehicle. So it sort of evolved from this. We didn't set out at the beginning to say, okay, we've done all this work before. Now we're going to start from scratch and make an autonomous.
So there was like no particular event where you're like, aha, I should move into like urban environments. It sort of was just a gradual evolution.
Well, the reason why we sort of moved, the steps sort of came at one point when the university was trying to work out what was going to happen with transport to the campus. So there was going to be a new train station. They wanted it to be on the campus, but it turned out not to be. It's about 2 or 3 kilometres away. And the result of that meant that there's now more people that are coming from just out of walking range to get to the university. So the question that they were asking at this time is, well, what can we do to solve that last mile problem? How can we take these people from these train stations that are just a little bit too far for a normal person to walk and move them into the campus, or move them from one side of the campus to the other? Because the University of Sydney is quite a large campus. It might be, I don't know, a good 20-minute walk from one side to the other.
It's huge. Yep.
Yeah, a good 20-minute walk from one side to the other. And so we got some funding from the university and from a number of different places to actually get our small electric vehicles, which we purchased, which we got under this project with the goal of automating them. And so that's the point when we sort of shifted from basically everything else surrounding the automation to actually applying it to the vehicles.
Awesome. So I didn't know that, and that's really cool.
Yeah.
Yeah. One like really good, I think that's quite a good little hustle, but at the same time, like a good application of the technology.
Well, but see, and the other thing is that the university is building buildings now that need to operate in 50 years' time. Like, they're going to be here for a long time. And it's pretty clear that the way that we move around is going to change somewhat dramatically. And it's whether to say autonomous cars will be here 5 years or whatever, it's not really the point. 50 years is a very, very long time. So if they can have a bit of an understanding about how that might impact the way that they need to design their buildings or design the infrastructure around the buildings, this would be a very good outcome for them.
Yeah. I mean, I don't know what other people think, but I think this technology is the way, like one of the future techs that's on the horizon. It's coming.
Yeah.
And but we'll get to that in a bit. All right. So So a question that I thought up to ask you, and I'm just this is purely out of curiosity, my own curiosity, is can you give us a brief history of autonomous driving in general? Have you researched that much?
Yeah.
I know people have been doing work on this for a very long time. So it predates this current excitement around machine learning. It's been...
Yeah, no, absolutely. So people have been doing, there's dreams of autonomous cars since, for a very, very long time, the 50s or the 60s or so.
Mm-hmm.
And even in the 80s, they were having, actual applications of cars, even with, computers that you would never imagine could solve these kinds of problems. Cameras that weren't even digital cameras, right? Analog cameras to do lane detection, stuff like this. And one of the biggest challenges with autonomous driving is that solving this 80 or 90% of the problem is actually not very hard. So to get a car to follow a lane, for whatever reason, you might use some cameras or some LiDAR or whatever it happens to be, or some magnets embedded in the road, or whatever your strategy might be, right? So there's been a lot of people that have worked over the last 50 years towards lane following, detecting an obstacle and stopping for an obstacle. And these aren't the hard problems. These are the very, very easy problems. And they've become engineering problems. So you can take a car these days, put some pretty basic sensors on it, control it even through a CAN bus or something, and then actually get it to drive, do something line following, and do some simple things. That's the easy part. And they've been doing that for a really long time. Mm-hmm. But the problem, it's the same problem that I think started originally with natural language and audio detection, recognition of voice and things like this. Because they solved a lot of those problems a long time ago as well. And they thought always, in the 60s, well, they thought, by the 70s, natural language stuff would be solved because we've worked out how it all works. And, but then these dates just kept moving forward and moving forward. And it was only when they started to implement these problems, solve these problems using machine learning, that they managed to get this massive increase. Because it turns out that it's an extremely high dimensional problem. And the only way that you can solve it is with a system, like a nonlinear optimized system, like a black box, neural network or so, with a very, very large number of dimensions.
Awesome.
So same thing goes with the cars, right? So there's many of the problems that you can solve, but those last problems about detecting the thing on the side of the road, is it a person or a rubbish bin or a chair or something, to do that very reliably is extremely hard.
And I think there's a question lined up covering just that in a couple of minutes. Okay, so I know you mentioned this right at the start of this, but you asked me not to mention it. But okay, so I know you're not directly involved, but a bit of left field. The name of this research center is the Australian Centre for Field Robotics. Is that correct?
That's the one. Yep.
That's where we are. Where I'm lucky enough to be recording this. So. One of the things that they actually have here is an autonomous submarine. I know you're not directly involved. Could you just talk a little bit about that?
Yeah, no, absolutely. Well, no, it's not that I don't want to talk about it. It's just that I don't know if I can fully, bring across, the complexities of the challenges which they face. Because whilst all the things that we do, we have, we do use GPS, but we don't rely on it, but we use other things. We detect, use lasers, and we use, radio communications to talk between things. And when you go underwater, most of these problems are significantly harder. Like you can't get a modem with a high bandwidth to talk between things. You can't use, the sensors that you use don't have the kind of precision like a laser would have precision. There is absolutely no GPS underwater. So the challenges that they have to deal with there involve using things like cameras to see what's on the floor and actually then make maps as they go using SLAM simultaneous. They have to simultaneously localize and map as they go. And what they're trying to do and what they're trying to achieve in these things is to generate science outcomes. So they want to be able to map an area. So they drop off the autonomous sub. It can go under the water, carry out a mission that they had planned in advance, and maybe 2 years later come back and do the same place and actually see how the things have changed, so that they can see how the plants and all the other things they can detect have changed. But no, it's fascinating. But it's hard because those things float through the water, and there's currents and other things that cause things to drift, and it's really, really hard to work out exactly where you are.
Yeah, it sounds. I guess would you say that? Again, I don't know if you can comment on this, but being in 3 dimensions as opposed to kind of 2 dimensions when you're on the road?
Yeah, many problems are solved by reducing your dimensionality. And so cars don't go up and down. They only go, in 2 planes. Yeah. So in a plane of 2 dimensions. And so, yes, absolutely. It's much harder to do it in 3. Yeah.
But it must be, equally as exciting. One of the things I mentioned when I was last here, that I saw when I was last here, is that your cars that you're using to build your autonomous systems downstairs are they're equipped with heaps of sensors. So you got everything. You got like the full works on there. I think you have LiDAR, you got like ultrasound, you have, like you just mentioned before, GPS. You got inertial as well, yeah?
Yeah, no, absolutely. We have inertial. We have a scanning LiDAR with 16 or 32 beams. One car has one car has the other. We have a range of cameras.
Yep, cameras.
Like an array of cameras that pretty much give us 360-degree view of what's going on around.
We have computers and stuff.
Yeah, we've got several computers in there. One of them is an NVIDIA Drive computer, which has significant compute GPU sort of power for handling sort of images in sort of highly paralleled stuff. So there's a lot of capability in the system, and we do log when we log data. There is quite a lot of it.
So, where I wanted to go with that is, are you guys currently taking the approach here where you throw as many sensors as you can at the problem, and then sort of like through, I guess, natural selection almost, another optimization technique, you use that to sort of weed out which like sensors are yielding the best, I guess, overall strategy, or?
Yep. So to handle this large amount of data, it's fairly expensive to put these kinds of sensors on a vehicle. And so if you wanted to make a car that you could mass produce, it's unlikely that you would be able to have this array of sensors. But having said that, the price of these sensors are coming down by a lot. And so LiDARs probably in the next 5 to 10 years are going to be probably an order of magnitude cheaper than they are now, with solid state LiDARs and other sort of innovations that are coming through in that space. But we're effectively, whilst we do this automation and we try to demonstrate these autonomous capabilities, we're a research group. And so we've got people researching a range of different ways of solving sometimes similar problems. And in the end, to make a robust solution to a problem, you probably won't be able to get away without using more than one sensor modality. So, you might detect things with a LiDAR and a camera, and then look at the consensus between the two before you make a decision.
Right. I mean, as humans, we do this too.
That's right.
We have more than one sense that we use to make decisions on a day-to-day basis.
Yeah. So it's not just for the research where we say, well, what can we do with each of these sensors? It's also, we'd try to reduce the number of sensors that we would put into, let's say, a final product, as you'd say. But you need to have these other sensors to be able to validate that technology anyway. You can't just rely on this. You need to have something else
100%.
to be able to validate what it is that you've been doing with the other sensors.
So you just mentioned the word that I was looking for before, which is robust. Is there any, with the current sort of sensor suite that you have on these vehicles, is there any leading candidate, if you will, of combination of sensors that you think might be a potential winner?
Yeah, no, that's a very good question. So we do quite heavily rely on LiDAR.
Okay.
We do this mainly because it gives us a very good, ground truth for all the other things that we use. It gives very good range, whereas anything else that comes from, let's say, a stereo camera or something else is going to be much more noisy in terms of depth perceiving depth. Problems is an active sensor, and it does, whilst it does work very well at, let's say, night because it produces its own light, there are issues when it's foggy. There's issues when it's rain. Fog is very bad for a LiDAR. Rain is not great for a LiDAR either, depending on sort of how big the drops are. And so there's no real way that you can solve your problem using just LiDAR alone, given that it won't work in certain circumstances. But having said that, same problem sort of arises for cameras, because if it's too dark, or if there's some other lighting problems, for example, if you're driving towards the sun when it's low on the horizon, cameras can have massive problems like this as well. And so it's going to turn out that if you want to make it so that your vehicle can drive in any condition, you will not be able to rely on just one sensor. The other one that's very popular is radar. So radar is one that's used a lot in automotive sort of applications. Problem with radar is that, well, for one thing, it's very, very noisy, and it requires significant effort to process. But having said that, it does see through pretty much all weather conditions. So if you look at the output of a LiDAR point cloud, you can see the shape of stuff. If you look at the output of a radar, you'll see blobs and sometimes blobs when there are no things there. Big cracks in the road might show up as a big radar reflection.
Right. Sure.
Which can be obviously big problem.
Okay, cool. So in your opinion then, LiDAR and radar are both very good candidates at the moment.
Yeah, look, I think the challenge with LiDAR is probably cost is the main reason why all of the major automation efforts, well, maybe minus Tesla, but all of the other major automation sort of vehicles are using LiDAR.
Okay, cool.
And other sensors as well, but LiDAR is included in this.
Okay, cool. Which leads on to my next question, which is around the perception, computer vision-based approach. How successful do you think a system might be if it's just purely vision-based?
Yeah, I think that so there are a number of sort of technologies using vision already that can do many things, like detection of street signs, lane detection, lane tracking, and these kinds of things. And there are a lot of people that have done very good work with visual odometry to even work out how you're moving through a scene. So there's different types of approaches to using this one, other than the obvious ones of detecting a person or a car or these things. They're very good at doing these. The challenges is that whilst they can show very good results with many situations, they don't really tend to have the similar performance when the conditions are not good. So, same problem with the LiDAR. If it started to rain, or if it's foggy, or if the lighting conditions are bad, if it's the sunrise or sunset, it's the same problems that people have when they're trying to drive.
Yeah, right. I mean,
the sun's shooting right in your eye, you can't see a thing.
Yeah,
right?
yeah, sure.
So these are all problems, and they're all challenges. So I think that vision can be used very well when the conditions are right. When it's not right, there's still a lot of work going into this, but I don't think at this stage it's prepared as an all-weather, all environment type of sensor.
Right. Cool. And to me, again, my personal thoughts on this is, I think as well, it makes sense that if you're going to you can use certain sensors to address, I don't know, if you've got the sun shining straight in your eyes, you can switch to a different sensor suite as a primary thing using to make decisions or whatever.
I think the most important thing is to actually know when it's failing. So the hardest thing is if you don't know, if you're getting information that you think is good, but is not good, that's a disaster. Okay. If you know it's not good, you can at least stop moving, right? You can pull over to the side if you can, or do something to stop. But if you don't know if you're getting good information or not, that you're blind. And
how do you go about choosing those thresholds?
Well, that's pretty much entirely the problem, right?
Yeah,
so
right.
If your detector is very good, but let's say when the conditions are bad, it's not so good. It's about understanding when it's not working and which settings it would work at. And you do this by gathering lots of data and just testing.
And can I ask what sort of tests you use? Are there certain, I don't know, metrics, certain graphs that you, names of graphs? Can you elaborate on that?
Yeah. Well, maybe not with the vision, but we do a lot more work with, with vision, there's a whole range of different ones, right? So you can get situations where you hand label stuff, and then you can use that hand labeled picture to then validate what your machine learning tool can find.
Sure.
So that's one way to do it. But it's very, very time consuming because it means hand labeling is an extremely intensive.
It's the most expensive thing where you could do it. Yeah.
So one of the ways that we get around this, and this was at the presentation that we gave at Tesla. This was Wei's presentation after my one. Is that we do something where we use a laser to detect things like, say, for example, the ground, and then we project that into the image frame, and then we use that to validate the image frame, the information that we get from the image frame. So the idea of this is that you can automatically make labels for things using one sensor modality, and then compare how well it works in the other sensor modality.
Really, really clever.
Well, without that, it's something somewhat impossible to do. And the other thing that we've done is that we've published a data set, which is of us driving around the campus. And we did this, I didn't personally drive most of them, but we as a group, we drove around the campus once a week for, I think, 70 weeks so far. And each one of those data sets we're publishing online. It's available for anybody to sort of download and use.
Awesome. I'm sure someone's going to find that useful.
Well, I hope so.
Can you whilst we're recording, can you if I was to go look for that, where could I find it? Your data set.
So we're actually publishing it to a magazine, the ITS magazine, which it hasn't been published there yet, but the data set is available. Actually, I don't know, maybe we can put this. Can you put this on the website, perhaps?
Sure.
Otherwise, I actually need to make sure I get the name right. But
post-production, I'll record it in.
Yeah,
sure.
Yeah, but it's a really good resource because you can download these. They're stored in ROS format, so basically most people can use the robot operating system for this. So they're big bag files, and there's a whole bunch of scripts to let you play back what's happening and then visualize what the car was doing and what was happening around it.
Cool. Yeah, I'm sure that would be super useful to some other people out there. Yeah, cool. So just to keep talking about, you mentioned this just a few minutes ago with regards to historically we've been able to solve these problems. We've been able to, that old 80-20 principle, the Apollo principle, I think it's called, or something like that.
I think so, yeah.
But anyways, you get to 80%, I don't know, in the 60s with technology then, but those last 20% is extremely hard to solve. So recently, I think Tesla did a presentation this year with regards to trying to solve the outliers or the tails. They're talking about the tails in a statistical distribution here, not tails on a dog. Statistical. Do you think that sort of trying to engineer to find the tails? So the whole idea with their system was, I think, to like whenever you have like, I don't know, a freak incident, like say you're driving along a freeway and someone throws a pot plant off a bridge or something. That's a freak incident. Do you think engineering a system where you keep capturing random events like that is a potential way of solving the problem of sort of outliers, or do you think additional breakthroughs are required in the machine learning space?
Yeah, no, it's an excellent question, and I guess it's pretty much one of the main reasons why you don't see them on the road right now. So there's been a lot of work done in trying to sort of simulate as much as you can these kinds of problems and outlier events. The problem is that you can record data and then use it to learn a model of something, but if the data is an outlier, the model is going to probably disregard it in the end anyway. Like you need to have something trained properly, you need to have a good sample set for each of the cases that you expect to use. So if your sample is an outlier, it's not going to end up making it into the model. So that's the first problem. So the other way to do it is to like focus on the outliers and see if you can solve them all individually. Maybe there's a subset of these things that you can, well, if this happens, we'll detect that and put as an edge case in manually or something like this. But the problem is where do you finish with that? Like how far do you go? And the way I've always thought about this is that you can detect people as much as you want, but not so much in Australia. But if you're in the US, like what about on Halloween when everyone's wearing crazy costumes, right? And nobody looks like people anymore. So all of a sudden you think, well, it works all the time, and if all your data is with people dressed normally, and then one day of the year people are wearing funny costumes, like how do you solve that? And they're excellent questions, and a lot of them aren't really solved at the moment.
Okay, cool. That's kind of like the next one I was going to ask, and you pretty much like brought up the perfect example, which is like, do you think to get to full autonomy, do you think we need to sort of do we need to make in this case cars? Do we need to make cars reason? Like solve the reason problem with machine learning. So for example, you just mentioned it before. Like I could reason that if someone's working past and they're wearing a costume, I could sort of infer from my previous knowledge that is probably a human dressed in a costume. Do you think we need to be able to get to that whole level of AI, if you want to call it that, before we can get full autonomous systems, or do you think we can solve it before that?
Yeah, no, look, again, these are all very good questions. I think that, there's going to be some point which these things operate safe enough. And to sort of preface where I'm going with this is that, cars have accidents now and they have lots of them. So there are a lot of people that get hurt and killed every year in cars. So the problem is not that we have this perfect system, we're going to replace it by something which may be imperfect. So we have an imperfect system already, and we're 100%. Hoping to sort of replicate that at least to the point where we're doing a better job.
Yeah.
And so what we're really hoping to achieve is that if a car can sort of drive in a way that is safer than a human, maybe this is the point at which we say, well, this is probably acceptable to use it. The hard part is working out when that line happens. And cars are quite lucky because road rules are very well defined. The problem is that it's the other users of the road that don't follow the rules, which is the main things that we have to sort of handle. If everybody followed the rules and every person crossed at an intersection when they were supposed to cross, these problems wouldn't exist.
Right. So do you think then, like, in your presentation, I'm pretty sure you addressed pedestrians crossing the road, like at some point. Like, do you think tackling each sort of sub-problem that we can think of individually and building that into a super system is the way to go in that case?
Yeah, no, I think that's probably the best way to...
Sort of engineering it?
Yeah, well, in the end, it's going to be an engineered solution.
It has to be, yeah.
I think the biggest mistake is it's not maybe the biggest mistake. So there are a number of people who try to approach this problem from an end-to-end machine learning strategy, right? Where you just say, well, if I just take the camera and I work out what the driver did with the steering wheel, then I'll end up with a model that tells me like how fast to move the pedals and where.
So like reinforcement learning or something, yeah.
Well, yeah, it's sort of in this way. Yeah. But to basically use this to then build a model of how to drive a car, and these models work reasonably well. But the problem is that they're very high dimensional, and it's very unexplainable. Like you can't tell me. Like if it fails, why did it fail? Oh, because this neuron didn't fire at the right time, or this thing, was a bit different than the training examples. And there's so many dimensions to the problem So you can't just expect that you can have such a ridiculously high dimensional problem and then just squash it all into one little box and solve a problem. Because there are things that we know about how cars drive. There are things that we know about how people move that we can use to our advantage. It's not that people can't move directly up. They generally walk forwards. Cars drive on in between lanes.
Right.
It's not like we need to start completely from scratch. And I think that engineering is the best way to solve this problem, because you can look at it from each system separately, prove and validate each one, work out how you can have two different ways of doing the same things for increasing the robustness to solve a problem, without just throwing all the things that we know about vehicle motion and people motion and all the other stuff away and just going, let's just pretend like we don't have a clue what's going on.
Yeah.
Well, that's my feeling on the matter. Though.
Yeah, I think
that's my opinion.
So I'm an electrical engineer by training, and I guess this year I've just become a massive convert to the engineering approach in software systems. So especially with this sort of discussion we're having here, and you pretty much mentioned it. You pretty much answered this last one, but so with regards to these systems, there's been a lot of talk around the whole safety thing. For example, I don't know, say an autonomous vehicle that's testing somewhere in America has an accident. It gets a lot of media attention, whereas these accidents happening every day around the world, they get no attention at all. What do you have to say around the whole safety part? Like you pretty much started talking about it just before, where why not use systems that are safer, that even if they're 5% safer or whatever?
Yeah. I think, there's reasons both technical and I wouldn't say political, but the worst thing that could happen for autonomous cars would be for a series of high profile, fatalities.
Yeah, right.
Because I think that would be devastating. At the moment, I think one of the biggest challenges in autonomous driving is that it's been very, very heavily promoted. And just about every company that works in it says, within 5 years, we're going to have solved it. And then, you have a startup that says, within 2 years, we will have solved it. And, I don't feel that that's a very realistic view of the problem, because I don't think you're all going to solve all the problems. You might get some way to solving them. You might solve some of the problems. You might make it work on a highway. I think probably the first things that we're going to see is in very restricted environments, like, for example, a highway where you don't have people wandering. If someone's wandering on the edge of the highway, that's a risk. When you're going at these speeds and things like this. So most highways are designed for cars to travel fast. They're going in the same direction. They're usually lane marked very well. People aren't allowed on them. And so if you start restricting the problems to these and solve them for these problems, then work towards the harder problems. Like, for example, an urban busy intersection with roadworks and
roadworks.
Yeah, well, it's like outside right now. That's right. And ones where you have outside school zones with kids that just wander out on the roads all the time.
So essentially engineering it.
Yeah, exactly. And understanding when you know that it's going to work and when you know that it's not going to work. And the challenge is, though, and I think this is probably one of the biggest challenges in the industry, is how you make a good business proposition about this to keep spending the money to do things which may not make a very good business model.
Interesting. And do you have any thoughts on that?
Well, the way that we've always approached this problem is that when we're back doing even the mining stuff, we were doing mining stuff where we're saying, well, let's train the operators to, let's see if we can give the operators more information to make better decisions. And then the question became, well, at which point do we say this is good enough that we should apply a brake ourselves? I think that the real benefits to doing this is that you can implement things along the way rather than going straight to level 5. No one touches anything.
Yep.
Along the way, I think there are massive gains to be had in terms of safety. I mean, I've been looking for cars recently, and cars you can buy now in the shops have road sign detectors for speed. And so they have a little indicator on your dashboard that says what speed you're going. And they have ones which do adaptive cruise control. So you follow the lane, but it will keep you the safe distance from the car that's in front. And you see the ones with Tesla where they do even more. They actually follow. I mean, other ones also do the lane following as well, but that's sort of the one that's attained the most, publicity, I guess, in this way. And you can follow the lane, and it can stay from the car in front. But you're still meant to be in charge if there's an intersection or if something strange is happening. So they're removing the driver from making many of the simpler decisions and leaving the driver in charge of making the more complicated decisions. That thing on the side of the road, is that a person or is it a kid going to step out, or is it, you know, a street sign with a picture of a kid on it or something, you know, this kind of stuff.
Okay, so
I see that being a really interesting way to actually step through this, to end up with more and more confidence in all of these systems that are involved in making these decisions.
So to engineer it and to sell it.
Yeah, that's right. Because you have to sell it. If you can't sell it, then they're throwing billions and billions of dollars. And until you can make money from it, those billions of dollars are just, they're really good ideas.
Research dollars, yeah.
And they're just research dollars.
Yeah, okay.
That's right.
Cool. Well, yeah, I think it's a fantastic place to end. Is there anything else you'd like to add, or?
Look, I have to say that whilst I've been working on sort of these similar things for a long time, it's a very good area to be involved in. I think that, machine learning is definitely going to be involved in parts of the solution to this problem. And whilst I say, we need to engineer things, and engineering and machine learning don't often go very well together, given the fact that an engineered solution generally needs to be more explainable than what you'll get out of a black box that you've trained with some data that you can't really prove for all circumstances. But having said that, I mean, even some of the research that we're doing now is on how to make this more explainable and how to break open these boxes to start to show, and I've seen other work that's sort of similar to this, but how can you break open these black boxes and then, or use them as modules in a system whereby, you've proved it works to a certain level that's acceptable to make it into a product. So it's sort of engineering them into things. So I think, the engineering behind it is fascinating, and the machine learning and the interaction is going to be very important in the future.
Cool. Are you looking for PhD students or masters at the moment?
Look, we're always open for PhD people that want to come and do a PhD with us, because, like we say, we do most of the different areas of this, and there's a lot of work still to be done. So yes, absolutely.
Cool. Just find you through your website, huh?
Yeah, and hopefully, I don't know whether the link for this will have a link to my page, but I'll try and put the one to the data set and also my page as well.
Too easy. Cool. Well, thanks for coming on today, and we'll be in touch.
No problem. Thank you very much.
Hi, everyone. Paul here again. I hope you enjoyed that episode. If you did, please feel free to help us out by clicking or subscribing at your nearest podcast provider, as that would really help us out. Cheers, and see you next time.